Howdy and welcome back. In this video of the lesson, we're going to explore how lambda expressions are effectively syntactic sugar for function objects. So before we kind of get into the details of this slide, I just want to step back and familiarize or rediscuss something we've seen throughout the semester. We've been defining and interacting with different class definitions throughout more or less the whole course. What we've effectively set up is that our class definitions provide a blueprint from which objects can be derived, right? This makes sense. Once you have that class definition, you have that blueprint and you can begin building up, say, a bunch of different movie objects that store information about, I don't know, your favorite movies or historical classics, what have you. Okay, here's what happens with a lambda expression. So as you're writing your code, you realize you need a function that returns a bool, takes a movie object, and it's going to be used in some sort of filtering operation. So you go, okay, I'm going to write a lambda expression that will say I only want movies with the release year of less than 1990. And I pass that maybe to my filter movies function that we've defined together, or I might go ahead and pass that maybe to the copy if standard template library algorithm. But irrespective, I've written in both cases a lambda expression. Now, when I go to compile my code, the compiler is going to take your lambda expression and it's going to generate a class from it, which has the call operator defined for it. In this case, that class is going to become known as a closure class. And then at runtime, from that template, because this is just, it's a class, it has a special name because we're talking about it in a special context, but from that, closures can be generated. And you can think about a closure as simply an object, which can be used and passed to our filter function, our standard library copy of function, etc. So a closure class is a class from which a closure is instantiated. Each lambda expression that we write within our code is going to cause the compiler to generate a unique closure class. The statements inside a lambda become executable instructions in the member functions of its closure class. So right now I want to ignore the closure clause of our lambda expression and just focus on the lambda expression as it presents here. So in this case, we have a lambda. In the parameter list, it's taking a movie by reference to const, and the body is simply returning whether or not that movie has a release year less than 1990. How this would be invoked within, say, our program, we could do something like auto. What do you want to call it? Foo? Let's call it foo for fun. Foo is equal to that lambda expression. So these things are assignable, and we can assign it to a variable. Cool. If I were to then invoke foo with, say, so this is after we've initialized foo with this lambda function, we can then go ahead and invoke it. So let's pass in m, assuming m is some sort of movie. At that point, what we would expect is that movie to be evaluated per the body of our lambda expression. And it will be. In this case, if movie m's release year is less than 1990, foo would return true, false otherwise. But how do we get to this point? What's actually happening behind the scenes? Well, you write this, and the compiler is going to generate that being this closure class, which you can just think about it as a class if the closures prefix is kind of throwing you off. But this is going to be a unique class for this lambda expression. Who knows what it's named? I just named it functor because that's kind of short for function object. But anywho, let's continue on. So this class is generated. To get the behavior that I just described, what would you have to do? So notice foo is initialized with our lambda expression. Notice that to kind of invoke the lambda expression after it's been assigned to foo, I'm using the call operator. This resembles exactly what we saw for our function objects, right? Notice here that we're not kind of constructing this in any special way. There's no sort of initialization that we saw with our released before function object that we discussed, I believe, in the previous lesson. Notice here the compiler is simply doing a mapping. It's taking the parameter list and it's putting that parameter list in the definition of functor's call operator, which makes sense, right? Because when foo_m here is, when foo's invoked with the call operator, so it's an existing object, which function resolves to it? Well, the call operator. Likewise, notice that the compiler just went ahead and took the lambda body and threw it into the function body for the call operator. Now, are you any surprised that this behavior that we just observed up here is happening? Probably not, because again, it's pretty much just a function object that's being generated. So far what we've seen is the pathway as we go from lambda expression to closure class, which again, you can just think of as a class. And then from that class at runtime, an object will be generated and passed to our filter function. That object is going to be a function object. In this case, the terminology we're using to describe it, a closure. So let's go ahead and discuss first what happens when we have an empty closure clause. So in this case, how this is being structured is exactly what we just discussed on the previous side. So we can see here that the parameter list of our, and I guess before we get into this, let's just make it clear. You write this, compiler generates that. Okay, so again, this is kind of a mapping. It's what we're writing to what the compiler is generating. So again, function object is going to be kind of the result of this process. Let's go ahead and look at the closure class from which those objects will be derived. So starting with our lambda function, again, if we wanted to invoke lambda, in this case, lambda, after it's been initialized with our lambda expression, we just go ahead and invoke it. And again, what's going to happen if we passed it m? In this case, it is the call operator, which is going to be invoked because lambda is a function object. At this point, it exists, and it was built according to the closure class blueprint, which is this, which was generated from our lambda expression. So looking at this, as we kind of talked about, well, the parameter list is going to be the parameter list of the call operator. The lambda body, well, it's going to be the body of the call operator. And that's kind of how all of this is slowly coming together. So again, it's the process. Lambda expression, compiler generates it into a closure class. At runtime, a closure or an object is going to be derived from our closure class. Now let's go ahead and take a look at what happens when we have this capture by value. So in this case, the object captured is passed how a parameter is passed by value to a function. So here's the setup. This is what you wrote, or you write, however you want to think about it. So within the scope where we're introducing this variable named lambda, we've also introduced a variable named year, which is storing the year 1950. Now notice that lambda is going to be bound to a lambda expression. It's how it's going to be initialized with. The closure clause in this case was passed year, which is within kind of the surrounding scope of our lambda expression. Okay, we'll see how what the compiler's generated is different in this case, but everything else looks relatively the same to our no capturing version of this, with the caveat that instead of having 1950, year is used in the comparison. So what's going on? You can think about the closure clause as being involved in the construction of the function object. It's going to be kind of present in the actual construction of the object from our class. So of the closure from the closure class. So here, what's happened is the code that the compiler generates will now not only have a call operator defined for it, but it's also going to have a parameterized constructor. Notice here that the compiler inferred that the type of argument to the parameterized constructor is going to be an unsigned int, and it's going to be used to pass in year. Okay, notice here that a private data member, year, is simply going to be used to, is going to be initialized with that argument. I want to point out right now, as the compiler is generating this, who knows what the names of these are? I'm just trying to make this intuitive so you can see the mapping here. So you can almost think about what's presenting within the closure clause as the arguments to the parameterized constructor that is going to be generated by the compiler. Okay. So now, just as we saw before, so let me just do that year, and the parameter list. So we can see how all of that's kind of related. Maybe let's do some different colors to make it so. So year is being used to initialize the year parameter. Cool, so now we're set up. Now this is almost identical to the function object released by that we created in the previous lesson, right? We were able to create function objects such as released by, and then we had to come up with a name. It's just called RB and say 1980. And in that case, the parameterized constructor was invoked. And then we said that we could like pass it movie objects, right? Because RB was callable. So you could do something like RB of M. And if M's release year was less than the year 1980, call operator would return true, false otherwise. And what we saw with all that work to generate that, the compiler did for us through our Lambda expression. I mean, if you look at the definition of the closure class functor, it's going to be pretty much identical to that of the callable of the released by function object that was created in the previous lesson. So the class that allowed us to create function objects such as RB here. Okay, and then everything else kind of in our Lambda expression is mapping as you would expect. So the parameter list is being used again to structure the call operator's parameter list. And well, yep, as one might suspect, the Lambda body being used to structure the body of our call operator. So hopefully you see what's doing here. This is very similar to the released by that we introduced in the previous lesson. It's just that whole function object is being created for us and behind the scenes by the compiler. Now, one important thing to keep in mind, and it's where kind of this deviates a little bit, and perhaps I should have been explicit here, is that in the definition we wrote here, the data member is actually going to be a constant unsigned int. It's going to be read-only. And let me show you. So we have some sort of Lambda expression. It's capturing by value. We're using it to initialize some sort of variable Lambda. And the function body is just plussing the year by 1 each time Lambda is invoked. Because again, what's presenting within the Lambda body is only going to be executed when we invoke that function, the anonymous function here, the Lambda expression. Okay, so we can see, let's go ahead and try that. Notice this code doesn't compile. And what we're trying to do here is we're attempting to mutate that year variable, if you will, that year which was captured by value. So in this case, the compiler is going to say, can it assign to a variable captured by copy in a non-mutable Lambda? And it will even tell you where that's happening. If you'd like to be able to interact with the argument to, say, the function object during initialization, so that presenting in the capture clause of our Lambda expression, we need to communicate that. So if we wanted to use year and increment it or mutate the value being stored within the call operator, so within the Lambda body, we have to go ahead and say that the Lambda expression that we're creating is mutable. And this keyword will come directly after the parameter list. And upon doing so, the compiler will then allow you to mutate this data member, if you will, because it's being put into a function object, and that data member is being initialized by value with the argument. So in this case, 1955 is used to initialize the Lambda expressions year data member, if you will. And then when this Lambda function is invoked through the call operator, well, because we explicitly stated that it is mutable, those data members' values can change. So without mutable, everything here is const. If you say that the Lambda expression is mutable, so directly after the parameter list, all of the data members are, in that case, both read and write accessible. Okay, cool. Now I want to just talk briefly about this capturing by reference. So the object captured can be modified the same way as a parameter passed by reference to a function. So that's same setup here. We have an unsigned integer object year. It's initialized with the value 1950. And then we have our Lambda expression. Notice what's different here is that in the closure clause, we see an ampersand by year. And this is going to communicate that this object is going to be captured by reference, which means so you write this, compiler generates that. And notice here that because we're capturing by reference, the data member is actually going to be a reference. And this will be fine as long as we use the initializer list in the parameterized constructor to initialize year or bind the data member year to the argument passed to it. So if we go ahead and look, here's where year is getting assigned to. Let me make this a little bit more clear. So year, those are all associated with the object being captured by reference. And we can see that that object is being used to initialize the data member reference year. So at this point, year is simply another name within the scope of our Lambda expression to this year residing in the surrounding scope. So year here, it's just another name for that year object. So if you were to change its value within the Lambda body, that change would be reflected after we invoked our Lambda expression. So that change would be reflected outside of it. So just, continuing on here, everything else in this situation is more or less identical to what we saw. So building up the call operator, you can see that the compiler went and took the parameter list of our Lambda expression, used it as the parameter list to the generated call operator. And likewise, well, guess what? The body of the Lambda body was used as the body of the call operator. And again, the spin on this is that variable presenting in the surrounded scope was captured by the Lambda expression by reference, meaning any sorts of interactions with it within the Lambda body, if you're assigning to it, it will be reflected after that has been executed. And the changes will be reflected in the object bound to by year because, well, in the Lambda expressions body, year was just another name for the year residing in the surrounding scope. So I really hope this is all coming together. This video took a couple shots to do, and I hope the result here is that you're kind of seeing what's happening behind the scenes and how everything's interconnected. and really understanding the different parts of a Lambda expression, understanding what the compiler is doing with it. And then now we'll look into, well, Lambda expressions and filter movies. We'll actually see those closure objects being generated and used in practice. So again, the result was you write the Lambda expression, compiler generates the closure class. At runtime, a closure or an object is generated from that class and it's used. In our case, what we'll see here, that object is a function object and it gets passed to our filter movies function. And we can use it exactly as how we saw the function objects being used before, with the caveat that it is a Lambda expression. And due to that, we're going to need to go ahead and ensure that the parameter that is receiving it in the higher order function is of type standard template library. Function with a return type that matches that of the Lambda expression, a parameter list that also matches that of the Lambda expression. So with that, let's go ahead and look into the last video of the day.